There's also a hormonal component that contributes to the baroreflex. So we talked about the neural component of the baroreceptor reflex, so now let's briefly look at the hormonal component as well. And the regulation that's provided by hormones is slower, and it works over hours or even days, rather than the seconds to minutes like the neural response. So we'll just briefly go over this aspect of mean arterial pressure now, and then we'll go into much more detail in the spring in the renal block. So as we saw, the sympathetic nervous system stimulates secretion of a few different hormones. It stimulates release of norepinephrine into the plasma from the adrenal gland, and it stimulates the generation of angiotensin 2 regulated by renin release, and also vasopressin. So all of these hormones are released in response to an increase in the stimulation of the sympathetic nervous system in response to a decreased mean arterial pressure. The onset of the release of these hormones starts within about 2 to 3 minutes and will reach a steady state within about 10 to 15 minutes. But the actions can last over several days. So although these hormones take some time to start working, they provide a durable regulation of the mean arterial pressure. And in general, the actions of these hormones will support the neural component of the baroreflex. So these hormones will support what the sympathetic nervous system is trying to do. For example, these hormones cause vasoconstriction, which increases central venous pressure and ultimately mean arterial pressure. And in addition to their constricting effects on vascular smooth muscle, angiotensin and vasopressin also act on the kidney to cause retention of salt and water, causing an increase in the plasma volume, which leads to an increase in the central venous pressure and increase in preload, ultimately leading to an increase in mean arterial pressure. And because of the cellular processes that have to be activated, again, this doesn't happen immediately and takes hours to days to occur. So these hormones are complementing the sympathetic nervous system in their regulation of mean arterial pressures, but they use several different mechanisms, and some of those are focused in the kidney. So now let's briefly look at each of these hormones: norepinephrine, angiotensin, and vasopressin. The sympathetic neurotransmitters are norepinephrine and epinephrine, and they can have either constrictor or dilator effects on the vessels, depending on the presence or absence of constrictor or dilator receptors in those blood vessel walls. So norepinephrine is generally an especially powerful vasoconstrictor hormone. And when the sympathetic nervous system is stimulated in most parts of the body, the sympathetic nerve endings in the individual tissues release norepinephrine. So in vascular smooth muscle cells, norepinephrine binds to alpha-1 receptors and causes the smooth muscle cells to contract. And this vasoconstriction causes an increase in the total peripheral resistance and raises the mean arterial pressure. Epinephrine is not as potent of a vasoconstrictor, and in some tissues can even cause mild vasodilation depending on that receptor density. And remember that sympathetic nerves to the adrenal medulla also cause secretion of both norepinephrine and epinephrine into the blood, and those hormones are able to circulate throughout the body and cause the same effects on the circulation as with direct sympathetic stimulation. And again, their exact effect depends on the density and activity of the receptors, and that varies by tissue. The renin-angiotensin system regulates the mean arterial pressure by regulating resistance of the vessels as well as the blood volume. So let's just take a quick look at how that works. So the main way that angiotensin is regulated is by the release of the enzyme renin. And one of the ways that renin is released is by stimulation of the sympathetic nervous system, which does occur in the baroreceptor reflex. That renin is released from cells in the kidney, and it acts on angiotensinogen that is made in the liver and circulates freely in the plasma all the time, converting that angiotensinogen to angiotensin 1. Once there's angiotensin 1 circulating in the plasma, another enzyme called angiotensin converting enzyme, or ACE, which is found primarily in the vasculature of the lungs as well as the kidney, converts angiotensin 1 to the biologically active angiotensin 2. Angiotensin 2 has many biological actions, and it produces a series of responses in an attempt to restore arterial pressure back to the normal range. So one of those is vasoconstriction, so it increases the systemic vascular resistance. Other important responses involve the kidney and include increasing salt and fluid retention to increase blood volume and increase preload. And together, the increased systemic vascular resistance and increased preload lead to restoring the mean arterial pressure back to the normal range. And vasopressin, also known as arginine vasopressin, AVP, or antidiuretic hormone, ADH, also participates in the regulation of arterial blood pressure. So vasopressin is a hormone that is made in the hypothalamus, and it is transported via axons all the way down into the posterior pituitary. And it's secreted from the posterior pituitary into the bloodstream in response to sympathetic stimulation that's caused by decreased blood pressure and decreased blood volume. The reason that vasopressin has multiple names is because this hormone was discovered for a couple of different functions right around the same time. So it was discovered that this hormone acted in vascular systems on the arterioles, causing vasoconstriction and increased systemic vascular resistance, and therefore increased mean arterial pressure. And because of its pressor effects, it was called vasopressin. It was also discovered that this hormone acted on cells in the kidney to increase water absorption and fluid retention, reducing the loss of water in the urine and the rate of urine formation. And since a diuretic is something that increases the rate of urine formation, this hormone was called antidiuretic hormone. So here in the cardiovascular block, we'll call it vasopressin because we're interested in these constricting effects. And when we get to the renal block, we'll call it antidiuretic hormone. But know that this is the same hormone that acts to increase systemic vascular resistance and increase fluid retention to ultimately raise the mean arterial pressure.